So first quick revision, we studied about Oster's experiment. You know that, okay? Current carrying conductor behaves like a magnet. After that, we studied how to find the direction of the magnetic field for a straight current carrying wire. Right hand thumb rule or corkscrew rule, okay? So that also we have discussed. Then the next thing we studied was how to find the magnetic direction of the magnetic field, or sorry, plot the magnetic field for a current carrying loop. So in the loop, we used to take a small section which is to behave like a straight line. Today, our job will be, we'll still go ahead with the loops and we will see how to see the polarity. Okay, how to, now since a current carrying loop behaves like a magnet, you and I would be interested to know how to find out what is South Pole and how to find out what is North Pole, right? So we will be concentrating on, again, a current carrying loop. Everything that you study from here onwards are all related to each other, a current carrying loop, and our job will be to find out the direction of the magnetic pole. So let me make one loop first. So this is a loop, and we will replicate this diagram also. Right, and I'll replicate this diagram. So I have kept two loops, right? And though the book calls it as the clock face rule, I'll give you an easy way to identify. The book will call it as the clock face rule. Clock face rule, but we will take a very easy way, and by that you'll be able to identify everything. Right. So my job is to make the cell, and one I'll make it positive on this side, negative on this, and the other one I'll make positive on this side and negative on this. Okay, bacha? Right. So if that be the case, then let's plot the direction of the current. The current is going in this direction, then this direction, then this, and this, 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 right? This is my plus and this is my minus. And if I see on this side, this is plus and this is minus, make the diagrams and then we go ahead. Right? So two loops created. We are going to find out how both the loops are now carrying current, but the only difference is that the direction of current, the polarity of the current is opposite in both the loops, right? Okay. लूप थोड़ा गोलू बना है, दूसरा वाला लूप आधा फूला बैलून जैसा हो गया है. ठीक है, shall we? Right. To identify this, the best and easiest method, remember this abbreviation CWS. Just remember CWS. It will be not written in book, you will remember this, okay? CWS, and CWS stands for clockwise south. Clockwise south. Now what clockwise? As you view, okay? As I view clockwise. Now whom are you looking for clockwise? The current, okay? Now let's look at this loop. Right? The blackboard is right in front of you. How do you see the current going in this loop? Clockwise. So the side facing you is a south pole. CWS, clockwise south. Understood? What clockwise? Current clockwise. How? As you view, as I view, I am viewing it from this side. How do I see the current going? In clockwise manner. So this face of the loop is like this. See, the loop is like this. From this side, you are seeing south pole. So from the back side, it will be north pole. Anna? From the back side, how will you see? Anti-clockwise. Just imagine. Okay, I am moving my hand I am moving my hand anti-clockwise. How are you seeing my hand? So you are seeing South Pole and I am seeing North Pole. Okay. So the way to remember it, how this do it in clockwise rule is, they will actually show it in this manner, that the S actually points like this. South Pole. Here you understand, current is going in this direction. And here we will see what? North Pole. This is called the clockwise rule. But I feel CWS is much more easier. As you see from your side, if it is the South Pole, then what type of magnet are you seeing? You are seeing, oh sorry, what type of, which pole are you seeing? You are seeing South Pole. Clear? So in the first section, Oster's experiment, straight current carrying wire, right hand thumb rule, how to plot the magnetic field lines, that you have understood. For a loop, how to plot it, you have understood, and how to find the polarity. So if you view the current from your side as a South Pole, then the side facing you is a South Pole. Sorry, in clockwise, then the side facing you is a South Pole. And if you view the current anti-clockwise from your side, then the side facing you is North Pole. In fact, if you understand properly, this is the reverse side of that. This is the reverse side of that. Because if a magnet has a South Pole, the magnet has to have a North Pole. Yes or no? Done this much? Go ahead to our next topic. Okay. So now a little bit more advanced topic we will be studying, and we'll study a topic which is known as solenoid. Solenoid. Let us first understand what a solenoid is. Okay. So if you take any wire, right, this was, I was explaining grade 12. If you take any wire, the wire should be insulated, and if you make turns of this wire, just like you have the telephone receiver, right, and on that if you see these coils, this is called a solenoid, right? This is a pure solenoid arrangement, wire which has been turned into many coils, right? And the wire should be insulated. Some more important features we will add in solenoid. So a solenoid is an arrangement, right? A solenoid is an arrangement of closely wound insulated is very important, okay? Insulated copper wire. At grade 10 we learn it like this. You must have seen, if you have opened up old tape recorders or anything, you will always see one copper coil turned around. That is actually a solenoid. But you will now say, sir, you are saying insulated, but I saw it absolutely gold in color. That is copper which is powder coated and insulated. It is insulated. Have you understood? Like that coil is actually dipped into a solution and taken out. So the coil is actually insulated. You might see that the coil is naked copper. It's not naked copper, it is insulated. So a solenoid is an arrangement of closely wound insulated copper wire. So let me just make an attempt of making a solenoid. My solenoid will typically be copper coils which are actually closely wound. 2 points I will add from higher science. In this solenoid, the radius of a coil, is much less as compared to length of the coil. Remember this always. There are two things. In grade 12 we study that. One is length of the wire, one is length of the coil. Length of the coil is this length. The length of the wire is when you stretch it, right? So we are not talking about the length of the wire. A solenoid will have radius is almost negligible, means it will be almost like your pen springs, but many coils, right? And you will have large number of turns. So what all things do we see in a solenoid? One is, number one, closely wound insulated copper wire. Insulated is very important. Large number of turns, and the radius of each coil. Turn or coil means the same thing, huh, beta? If I say a solenoid has got 500 turns or has 500 coils, it means the same thing. The radius of each coil is much less as compared to length of the coil. That means the radius is almost negligible. Clear? So let's see what happens in a solenoid. Okay, so let's see the beauty of a solenoid. Right? Oh. Now this is a solenoid which I have connected to a EMF source. Say this is plus, this is minus. So let's put our current direction. Current is going in this direction. Obviously the current will come out in this direction. Children, if you're done drawing this much, then let me know. We will understand something more interesting. Have you seen in our compound walls of Pebble City around L Tower and K Tower backside, you see a lot of turns. So that is like a solenoid. Okay. More tight, but you can assume that that is like a solenoid. Okay, why I have said that you'll understand now. Now, what is the use of a solenoid, or what is its beauty all about? Okay, let's see. Are you done with this much of drawing? Right. Now, position yourself here. Position yourself here, right? So that your eyes are in this direction. This is your eye, and you are looking in this direction. Okay, look at my diagram now. Don't I see this solenoid as many loops? Yes. And let's look at the current. The current is going in this manner, going in this manner. I missed one. That's why the calculation is not coming up. Yeah. One minute. This is there. Now, look from this side. Try to stand on the boundary wall of our apartments and see that curled wire which is there, the barbed wire. How is the current going? Clockwise direction. Do you agree? The current is going in a clockwise direction as I see from this side. Now stand on this side and see how is the current coming? Anti-clockwise. So for each loop, there will be a south, backside is north. Again a south, backside is north. Again a south, back. So can't I imagine this like many fridge magnets back to back to back to back to back put together, right? So you basically see a south pole on this side and you see a north pole on this side, right? And the solenoid has a lovely feature here where it will be behaving like almost a bar magnet. In higher classes, you will study magnetic field outside a solenoid is zero. All the magnetic field is always concentrated inside the solenoid. Are you understanding? The solenoid is now behaving like a bar magnet, okay? And if I want to make it more interesting, so this is the north pole. So I would have my field lines which will be coming out from the north pole and joining at the south pole. At the south pole. And inside the magnet, the field lines are always uniform and they are always pointing from south pole to north pole. So you have actually created a bar magnet. You have actually created a bar magnet. So a solenoid behaves as a bar magnet. But there is some style in it. It is a bar magnet which is like a slave to me. I can magnetize it the moment I want, right? I can change its polarity by just changing the polarity of this current. I can change the polarity. demagnetize it the moment I want. And one more thing I can do is that I can increase or reduce the magnetization intensity. That we will now study how you can do. Okay. Children, tell me, when I taught you last class about properties of magnetic field lines, did I make you write one point that the concentration of lines at a point denotes the concentration of the magnetic field? Acha. So there has been an error with me. Can you just what do you call edit your notes for one small thing? Okay, just edit for this. It's a simple thing. This is my magnet. Okay, and let's say this is my north pole and this is my south pole. Magnetic field lines are coming out, going this side, coming out, going this side, coming out, going this side, coming out, on this side. Okay. Simple point, you'll understand. And inside the magnet, they are always uniform. Okay. The concentration of magnetic field lines at a place denotes the strength of the magnetic field. Concentration of magnetic field lines at any point denotes the strength of the magnetic field at that point. Concentration, should I write it? Concentration of magnetic field lines, concentration of magnetic field lines at a point denotes the strength of magnetic field at that point. So what I'm trying to say here is that say you select a point, say you at a point, or you can also replace this point by a word called region. Okay, so we'll select a region. You select a region, right? And in that region, okay, you have selected a region. If you find high concentration of field lines, then it indicates higher intensity of, yeah.
Sir, the strength is more near the poles of the path.
हाँ वो आएंगे अभी, यहीं से आ जाएगा. Intensity, higher intensity of magnetic field, right? So let's see what we have written. Let's try to understand that. Okay, now suppose you have fixed a region, a small circle. Say my circle is a x centimeter radius circle, and to make it very crystal clear so that we are so like I've taken this circle, okay, and this is the region, and cloned it and kept two circles. Now say suppose I take this circle, same area, and I'm trying to measure it, say at this region. How many field lines are crossing it? One field line is crossing, right? And say suppose I take the same area and now I check it here. How many field lines are crossing? Two field lines are crossing. So which region has more magnetic strength? This region has more magnetic strength. Are you understanding now? The magnetic strength at any particular region is given by the concentration of the field lines in that region. If more field lines are actually crossing through your selected region, more is the magnetization. Now, as Tegbir was saying, that the strength of the magnetic field is highest at the poles. Why? Because when you come to the poles, your chances, see, if I come to the poles, right? Let us take this 1 second, and you can bring it near to the poles. Your chances of getting the magnetic field lines is maximum. And that is not the story only with this. That story is also applicable if you would have come to the South Pole. Yes, very good. If you would come to the South Pole also, you find a lot of magnetic field lines. Now, do you understand? Strength. So you can, based on this, you can write one more point, that the strength of the magnetic field is highest at the poles. The strength of the magnetic field is highest at the poles. This is actually based on this study. The strength of the magnetic fields is highest at the poles. You understood why it is highest? Because whenever you sample a small region in a pole, then you find that the number of field lines crossing that region is maximum. Okay? So we go back to solenoid. Right. So we go back to solenoid now. So our solenoid is now exactly behaving like a bar magnet. Now we need to see how does the magnetization depend, because this is something artificial that you have created. So we will write here strength, write down strength of field depends upon A. First is the current. So in this you can write higher the current, higher is the magnetic field. Means more current you flow through, pass through the solenoid, more will be the magnetic field. Have you understood? Okay. Number 2, B, we call it as number of turns. Number of turns. So if your number of turns is usually denoted by N, so if your N goes up, your magnetization also goes up. That means if in a solenoid you have more number of turns, you will have more coil. Right? The third is the most interesting, C. C is introduction of a soft iron core. Soft iron is a type of iron, okay? Soft iron is a type of iron. Instead of leaving the solenoid vacant with air, you put one soft iron core inside it. Have you understood? You put one soft iron core inside it. Then soft iron core helps in concentration of magnetic field. So introduction of soft iron core, and this one helps in concentration of magnetic field. That means if you have a solenoid without any core, and if you have a solenoid with a core, which will behave as a better magnet? The one with a core will behave as a better magnet, because the soft iron core behaves as a concentrator of magnetic field. So instead of your solenoid wire just being like this, see, in the air, think of my hand as a soft iron core. You just make it like this. एक छोटा आयरन का पीस घुसा दो अंदर में, अभी ये जबरदस्त मैग्नेट बन जाएगा. Clear? Solenoid clear? What is a solenoid? A solenoid is an arrangement of closely wound large number of turns of insulated copper wire, where the radius of the turn is very less as compared to length of the coil. A solenoid behaves as a bar magnet as soon as a steady current flows through it. And the magnetization of the solenoid depends upon the current, directly proportional, number of turns, directly proportional, and introduction of a soft iron core, which helps in concentrating the magnetic field. So if you have a soft iron core, you have made a very good magnet. Clear so far? If you have understood this much, then please tell me. That you have to understand the metallurgy of this, which is not at your level. We have 3 types of things: paramagnetic, ferromagnetic, diamagnetic. So if you are diamagnetic, you magnetize, demagnetize very quickly. It helps in that. Magnetization means materials have got domains inside their body. So sometimes, have you seen, if you keep a pin with a magnet and then you take out the pin and you take the pin and go to another pin, it will still attract. So you are just making it a magnetization is very feeble. So I have aligned your domains, but again that gets aligned also. But suppose somebody should ask a question, sir, how to break the magnetization of a magnet? Do you know that? Suppose you have a bar magnet. One is hammering. Keep on hammering that thing, the magnetization will go away, because they are all aligned. You have to break that alignment. Okay? If we have understood this, then it is time for us now to prepare our slave. Our slave is now getting ready. Our jinn. So, time to understand something called an electromagnet. Electromagnet. So, let's see what is an electromagnet. Now, since you know a solenoid can be made as a magnet, so you have become very smart and you think that I can now make an electromagnet, and not do one mistake, that is, don't leave the coil of the solenoid vacant. So what you do, you have taken a soft iron core. What is this, beta? This is a soft iron core. And on this soft iron core, now you will be winding insulated copper wire. Right? There's a key. Switching on off control. So we'll have our cell. This is our key. The cell will give what? A steady current. Steady current. So now you have made an electromagnet. So electromagnet is an extension of solenoid. So how do we say what is an electromagnet? An arrangement where insulated, closely wound copper wire are wound over a soft iron core and a steady current is passed through. Steady current means direct current. Steady current is passed through. It's an electromagnet consists of a soft iron core on which insulated copper wires are closely wound. Right? It's basically a solenoid with a soft iron core. Shall we? Now write down an electromagnet. An electromagnet consists of a soft iron core. An electromagnet consists of a soft iron core. So it consists of a soft iron core, soft iron core on which insulated copper wire is wound, and then steady current is passed through it. Now this becomes a very strong magnet. Okay, very strong magnet. Understood? Now let's see factors which control the intensity of magnetization. Factors which control the intensity of magnetization of an electromagnet. Often क्या बच्चा? Electromagnet. You have already learned about solenoid, so you know here also. What will be the factors? You only tell me. How can you increase the magnetization of this solenoid, of this electromagnet? Increasing the current. Okay, next. Increasing the number of turns. Then now that you cannot add here. electromagnet by birth contains a soft iron core. No, that's the reason I actually said I had asked this question. See, in a solenoid, you have a choice to put the soft iron core, but in electromagnet, the soft iron core is inbuilt. So here, one of the parameter we will say is obviously the current. If the current goes up, the magnetic field also goes up, right? Number two, the cross-sectional area. Yeah, cross-sectional area has to be less. The number of turns goes up, B goes up. Cross-sectional area, that's the reason we always said that the radius of a solenoid is always negligible as compared to the length. So if the radius is small, then the cross-sectional area also gets reduced. Okay. One thing which we say here is, that's why I drew this diagram. The third point is interesting. The third is the reducing the length of the air gap between the ends. Reducing the length of the air gap between the ends. What does this mean? Now, if you you have to see the figure, otherwise you'll not understand. Reducing the length of the air gap. If you see, this is one end, this is one end. This much of length is there. But you just look at this sort of design. In this design, I have actually designed it in this manner. Oh, sorry. I have designed it okay.
Then how will that increase the band?
Now I'll tell you that those are beyond your scope now. For that, you have to understand properties of magnetization. Okay, but I'll give you an example in which you will understand. Look at this magnet, electromagnet. What is the length of the air gap now? This much. Have you heard about a horseshoe magnet? This is a horseshoe magnet shape. Horseshoe magnets are much more powerful as compared to bar magnets. This is a horseshoe magnet, but it's a horseshoe electromagnet. Have you understood? So one is increase the current. Number two, increase the number of turns. Cross-sectional area should be less, and more is the length of the air gap between the ends. The more you can actually draw it over like this also. आप ऐसे भी coil बना सकते हैं. I tried to make it more. You can just make it a jalebi over here. So ensure that the length is small. So you actually are making a horseshoe magnet out here, right? Brings us to our next question. Is shall I change? Okay, this brings us to our question, which is very common in CBSE, and this question is distinguish between an electromagnet and a permanent magnet. And to answer this, just think permanent magnet is your devil that you created. Electromagnet and permanent magnet, right? The first thing, intensity can be varied. What is the intensity? Magnetic field intensity, right? Intensity means magnetic. Here the intensity is constant and decays over time. A magnet will lose its magnetization. Here intensity is constant and thereafter decays over time. So a permanent magnet, have you seen a speaker? Speaker has got a magnet, a big circular magnet. Okay, so the intensity is going to be dying down. Number two, polarity can be reversed. Ye pura is your slave. Polarity can be reversed. Here what do we see? Polarity is fixed. Polarity is fixed. You cannot change the polarity of a permanent magnet. If it's a north pole south pole, it will remain a north pole south pole. Third, magnetization and demagnetization can be controlled. Have you gone to ATMs and other security doors where people say, wait, let me first put your fingerprint scanner, only then the door opens. So the door is actually a electromagnet. So the magnetization is locked. Have you understood? Then as soon as you put your fingerprint, demagnetization, it will open up. Great help on this magnetization. Then let's see one more thing. Have you seen these movies, some fight scenes which are happening in container yards? Container yards, you know, lots of containers will be there. Maersk and P&O, Ned Lloyd, all these containers will be there, and villain and hero running. So when these containers are placed in the container yard in a port, then our friend Ved must have brought one Jaguar. He must have brought a Jaguar or something from, or a Porsche from abroad. But his container is right now below something. So you'll have a crane who actually controls the whole thing, and then we will spot this is our 63rd container. Very quickly he will take each container and put here. Those containers also have magnetization. That they will magnetize, additional, pull it up, and wherever they want to release, demagnetize. Plus scrap lifting cranes. Have you seen scrap smelters? So there everything is iron. So they are all electromagnet controlled. So electromagnet will magnetize, demagnetize. So we say magnetization and demagnetization can be controlled. Here cannot be controlled. Can you ask a permanent magnet that forget your magnetization? No. So this fellow is basically your jinn or your genie whom you have created, and it is going to behave the way you want. Understood? Now one real life example. Otherwise you people will sleep. So, and this is something we used to make in projects a lot. This is the most simplest thing. The ding dong bell, calling bell. All right, we'll see how this works. In fact, if you open up the cheapest item, I don't think it has still, now it must have crossed 100 rupees. It used to be some 40-50 rupees. So how does a ding dong bell, for that you have to first understand how like the bell in my flat. What happens? As soon as we have a switch, as soon as you press the switch, you will hear ding. And as soon as you release, you hear the dong, ding dong, like that. Let's see how this happens, okay? So, typical story, it's an electromagnet type of story. So, what we will have, though not in your syllabus mein nahi hai, par interest hai, dekho kaise hota hai. So, we will have some sort of a, have you seen sewing machines? We use threads, like those threads come on a cardboard pipe. So imagine this is like a cardboard pipe, a small cardboard pipe. This is a rubber pipe on which your what you call the electromagnet has been turned like this. This is my electromagnet. Got it? Right. And then inside we will have our soft iron core, but our soft iron core is very stylish this time. Our soft iron core is not only a soft iron, but also is a very good hammer. It is a very good hammer, okay? It's an excellent hammer. It's an excellent hammer. And 1 minute. Such that both sides have been made like a hammer. Okay? Fine? Okay. Now we will have two sorts of highly sonorous plate. You know the word sonorous? Metals which will make noise, okay? Sonorous plate. And one more plate is here. Plate 1, plate 2, sonorous plates. Okay? Bored nahi ho raha to? Are you getting bored? Don't get bored. Even if you get bored, there is no other option. So this is the wire. Now see how mechanism happens. And let's say this is our battery. And then if you see the switches of call bells are very stylish. These switches have got 1 minute, huh, bacha? Arey. Call bell switches are spring-loaded switches, auto-release, not like your normal switches which you press and they go on press mode. Okay. Now see what happens. This sonorous plate is generally made up of magnetic material, and this will be made up of non-magnetic material. Magnetic material, non-magnetic material. Now see. Hello Ishita, where is your attention? What happened? Shreya also sitting and like, what happened? Beta, fever, sleep. So yes, please. Acha, you have cold. Now see what happens. Okay. As soon as you turn this switch, now this switch is a spring-loaded switch. Okay, this is a spring-loaded switch. As soon as you put in contact, the electromagnet magnetizes, right? The soft iron core will magnetize, and this part is the magnetic material. So when you switch it on, the hammer will go and strike here, right? So it will make the ding noise, correct? When you switch it off, क्यों आएगा वापस? Why will it come? No, I am here. I go, see, this is where your mechanics is failing. I'm here. You pushed me. So I went with the force out here. Now the force vanished. Why should I go back? You all are not thinking. That's where your science. No. That's where your science thinking is less. Now just think. Suppose I am here and you tie a rubber band behind my waist and you magnetize me. I just go and hit that ting. Magnetization gone. Now who will be taking control of me? Rubber band will take control of me. So I need a restoring force. That restoring force will be actually created. यही तो interest, यही तो mechanics नहीं समझते हो ना? That restoring force will be created by putting a spring out here. Have you understood? So when it gets magnetized, it will compress the spring and go. And once you lift your switch, मैं क्यों आया था? Why? So spring says, come back. Tong. Ting tong. It's making. Otherwise, the tong will not happen. मजा आया आपको ये? It will. This is just like your dot pen. Have you seen your dot pens? How does the click pens work? You press it against the spring. At that time, it turns and locks on one groove. Otherwise, it should not come up. Na? Whenever a pen does not retract, then we say spring badlo. So it will actually compress the spring, go and hit this bar and come back. Now, what happens? Why did they actually give you this type of switch? It's not just because for the ding dong. The other thing is that if you keep it pressed on, then large current will be flowing and it will heat up this particular coil. And if it heats up this coil, the bell is gone. It will fry the bell. So if you want to damage somebody's ding dong bell, not those bells, those jo bajane se om, those are all electronically controlled bells, not those. The plain ding dong, like my gharwala, but please don't do with me. Just keep the switch pressed. It will make a big spark, tapak, some spark will come and this will fry off in 1 minute. Press होके अंदर घुस गया, जल गया, वो होगा ही. So the only way is ding dong. And now since I have told you this, I should make sure that before leaving my flat, I deactivate that particular ding dong, what you call the MCB from the inside. Have you understood? It's a very, and we used to make this a lot in our science experiments. This is a very, very easy thing. You just switch it on, gets magnetized, compresses, goes, and with the spring compression comes back. ठीक है? Not in your syllabus, just for understanding purpose. But what you will be asked in your syllabus is this question comes a lot. Distinguish between an electromagnet and a permanent magnet. Just remember, electromagnet is your slave and you can control this magnetization the way you want. ठीक है? Our next topic is a little bit interesting. So I don't know, we have got still 15 minutes, so let's do. Next topic, I will not write the topic heading straight away. So let's, okay. Current carrying conductor. Okay, current carrying conductor. Current carrying conductor. Try to understand, because if I write the heading, it will confuse you. We will decode the heading easily. So this is me. What did you hear the word? Current carrying conductor. Current carrying conductor. What comes in your mind? It is nothing but a magnet. Yes or no? But I'm still not writing the word magnet. Current carrying conductor. Current carrying conductor placed in an external magnetic field. Let's try to understand this also. Current carrying conductor, which is actually a magnet, but I'm still calling it current carrying conductor, placed in an external magnetic field. So this external magnetic field can be a magnetic field which can be created by an electromagnet or a permanent magnet. Now try to read this statement from this side. यहाँ देखो, पहले लिखो, मन नहीं समझोगे. Try to read it from this side. There is an external magnetic field. There is an external magnetic field. That external magnetic field is due to an electromagnet or a permanent magnet. Say, suppose I have kept a magnet out here. Sir, what magnet you have kept? Permanent. No, sir, keep one electromagnet. Okay, kept an electromagnet. Turned on. So, is it not creating a magnetic field? It is creating a magnetic field. In its vicinity, I have brought a current carrying conductor who is also a magnet. A magnet in the vicinity of another magnetic field. Do you think there should be some interaction? In physics, what term will define that interaction? What interaction can be there? What interaction can be there? This is a current carrying wire. A current carrying wire is what? Magnet brought into the vicinity of another magnetic field. So do you think there should be some interaction? What is that interaction? You may be wrong. सोचो ना, क्या interaction? तुम्हें कैसे पता attraction होगा? Repulsion भी हो सकता है. तो इतना समझ में आ गया that we can have either attraction or repulsion. In physics, which term will actually define that? What terms defines you about attraction, repulsion? Go to grade 8. What is that physics quantity? If you are attracted to me in physics, what is the quantity that is bringing you to me? Force. Push, pull, force. So I'm completing the topic. Now you read it. Force on a current carrying conductor placed in an external magnetic field. So my best example is bhuka bachcha placed near a bhuka and one who loves food, somebody like me, make me very hungry and I love food. I am placed near a sweet shop. Will there be interaction between me and the sweet shop? Yes. I may go to the sweet shop, like it, attraction. I may taste one or two samples, I may dislike it, I may get away from the sweet shop, repulsion. Now, question is, if this external magnetic field, I make it fixed, that is, the sweet shop is made fixed, right? and you make this fellow movable, then what will you observe now? Then the current carrying conductor will do the movement. It will experience a force. It might either come or it might go away. Is this much understood in your head or not? If you have a current carrying conductor, you basically have a magnet. You are now putting that magnet into another external magnetic field. A hungry, foodalicious boy placed in front of a switch shop. We definitely expect some interaction. The switch shop is fixed, so it will be the boy who will either move to the switch shop or will run away from the switch shop. Understood? Our job here is to understand what is this force, how to find this force. Basically, in our grade 10, we will be interested on the direction of this force, which will actually open the pathway to understand something called Fleming's left-hand rule. Are parna hai to aise padho, Fleming's left-hand rule. So we'll see one small experimental setup. We will not discuss the left-hand rule, otherwise our friends will miss. So let's have one experimental setup, okay? And you can enjoy, you can draw it later also when you are at your home. So the experimental setup is something like this. I have got a physics stand of this manner, okay? And I also have a mild this thing, and here I have kept S hook sort of a thing, okay? I have kept a S hook. You understand what is a S hook? S hook, right? Like what do you have in your necklace backside? Same, S hook. And on this side, what I have done, our yesterday's diagram. So I have taken a ball like this, right? And I've kept this ball here, like in this manner. Understood? Right. Now I've done some interesting arrangement. What all arrangement I have done? I have taken a probe. And I have connected the probe from here, and I have brought it here. And I have put a cell out here, and then I have put a key right on this side. Fine. And on the other side, I have taken, this is all metallic, okay? So I have completed the circuit. I have completed the circuit, say in this manner. Right. Now, some more interesting things I have done. I have taken liquid mercury. And I have filled this so-called crucible or my tray with mercury. Why mercury? Mercury conducts electricity. And then I have taken a very fine, I have taken a very fine piece of copper wire, metallic copper wire, and I have put this, no, not copper wire, you can say a magnetic wire, and I have kept it on this side. Understood? Now we're going to study that same force on a current carrying conductor. Now the next thing is, okay, further what I have done, this red one is a magnetic substance, okay? Further what I have done is, I have taken a horseshoe magnet, and I have placed the horseshoe magnet out here. Okay. Clear? So let's understand our diagram once again. I have taken a stand, and on that stand I have put a magnetic stick. This is a magnetic stick, means a stick of magnetic material. It is not magnet, huh? It's a soft iron stick, the best way. It's a soft iron stick, which is right now dipped in the mercury. And look at the circuit. The circuit is such wired that it goes and enters into mercury. Mercury is a conductor, so the current must be flowing through it and actually comes through it if the switch is turned on. Now see the beauty. As soon as I turn on this switch, this red one thing, मैं तो magnet बन गया. Current flows through him. But as soon as you turn it on, don't you think the current will be flowing through this particular stick? Yes, the current will be flowing. And the stick says, I have become a magnet. And if he has become a magnet, means he has immediately become a hungry, food-delicious child. And there is a food shop. Got it? So immediately this stick will push out from this mercury, and suppose it's just touching the level of the mercury, it will just push out and get attracted towards this magnet. And then it will break the circuit. See the beautiful, he has undefined it. And then it will, once it gets out of mercury, so what happens? The best thing is, once you switch it on, this fellow will actually push off from this mercury because he gets magnetized. And once he gets magnetized, this horseshoe magnet tells him, Aja, Aja. And he comes here. Once he comes here, the circuit is broken. And he again says, huh? What happened? So he again goes back to the mercury. Once he gets into the mercury, he again gets magnetized. So he just karta rahega. This is the principle of those school bells which ring with. Have you seen? This principle is used. The hammer will go and strike the gong. As soon as the hammer strikes the gong, circuit is broken. So hammer comes back. Hammer comes back. Hammer touches the circuit. Go back. Go back. Come back. Go back. Come back. Go back. Come back. That buzzer that happens due to this. In our next class, we will study how to find the direction of force using Fleming's left-hand rule. So if you see in this entire show, three things were there. Three things were there in this entire show. Number one, you had a current. Yes or no? You had an external magnetic field. Yes or no? And you also had something which you want to find out, which is your quest. You basically want to find out, that is the force. So this fellow we call in electricity as I. This fellow in magnetism is B, and this fellow is S. So it's FBI, Federal Bureau of Investigation. And we will do this investigation in our next class, how to find out the direction of F. इसको क्या बोलते हैं? FBI. और यही है FBI. FBI. ठीक है? So did you understand what happens when force on a current carrying conductor? So current carrying conductor behaves like a magnet. Very stylishly it will be here. As soon as you switch on, मैं तो बन गया magnet trick. My magnetization gone trick. I got magnet trick. Trick. It will keep on doing. Okay, so we'll close today. Right on time. Thank you for joining and appreciate your time.